Continuing our theme of routing, in this video I'm going to tell you about a distance vector protocol. Distance vector protocols are one in which the routers maintain a vector of their distances to a given or to all of the other routers, and then iteratively through a distributed algorithm they converge on finding the shortest path or the lowest cost spanning tree from them to every other router. And we're going to see a specific example of this, what's known as the Bellman Ford algorithm, which is the most commonly used algorithm in these distance vector protocols. So the particular problem we're going to address is how can routers work together to find the minimum cost spanning tree. Here's an example that I've shown in green here as the minimum cost spanning tree for this particular graph. Notice that this is equivalent to finding the minimum cost spanning tree amongst just the routers. It didn't matter whether I included the end hosts, because really in the end we're just building the spanning tree amongst the routers. So in the rest of the examples I'm just going to confine myself to that. So now let's look at the distributed Bellman Ford algorithm. And in this example we're going to use the case of trying to find the minimum cost spanning tree to R8. Just to remind you, in the previous slide, this was the router in the bottom right-hand corner. So this green spanning tree shown here is the minimum cost spanning tree for everybody to reach R8. So remember that in general, all of the routers are going to be building the lowest cost spanning tree to reach all of the other routers. So we're just taking one specific case here of finding that minimum cost spanning tree to R8. So in the Bellman Ford algorithm, we're going to assume that the routers know the cost of the link to each of their neighbors, so that there is a metric and a cost associated with using that link. And we're going to assume that router R sub I is going to maintain the value of the cost to reach R8. So at any one instance, it's going to keep a sense of its current lowest cost to reach R sub 8. So router RA, that's going to be C sub I. So we're going to have a vector C, which is going to contain the 7 costs of the 7 routers R1 through R7 of their current cost to reach R8. And this is the distance vector to reach R8. Initially, the algorithm is going to set this vector to all values of infinity. And then every t seconds, so starting after the first t seconds, Ri is going to send Ci to its neighbors. In other words, each router is going to send the cost to reach R8 to each of its neighbors. If Ri at any time learns of a lower cost path, it's going to update this value C sub I. So if after t seconds it hears a lower cost path to reach R8, it's going to update its value, and then we're going to repeat, and we're just going to keep repeating forever. Okay, let's look at this as how this would work on the graph. And remember, there's a natural extension to calculate this for R1 through R7. We just exchange all of the values. I've just shown you the one example here. Now let's look at a concrete example. And we're going to look at this particular graph here, which I've annotated with some costs. They're different from the costs before. It doesn't matter the particular values or how they came about, whether they're for represent the delay of using a link or the price of using a link. They're just values, and we're going to try and find the minimum cost spanning tree using the Bellman Ford algorithm. So remember, in the Bellman Ford algorithm, we start out with the distance vector to reach R8 of all the values set to infinity. So R1 thinks it costs, it's infinite to start with, R2, and so on. They all think that the cost is infinite in order to reach R8. Okay, so that's where we're going to begin, and we're going to go through and see waves of information propagating through so that we can update these and steadily converge on what the minimum cost spanning tree is in order to reach R8. So in the next step, that information is going to propagate outwards from R8. So this information here is going to tell us in that first wave that R8 can be reached in one hop from these routers. R3 is going to learn that it can get there in 4. That's over the direct path. R5 will learn it can get there in 6. R6 over here will learn that it can get there in 2. And R7 will learn that it can get there in 1. So they're the costs in that first step. And so R3 will update its own value, 4, 6, 1, and 2, respectively. And now they will advertise those values on in the next round of the algorithm. So that information is going to propagate out here into the next hop. So R4 is going to learn in the next iteration of the algorithm that it can get there at a cost of 2 via R7. So 2 via R7. Could also get there at a cost of 6 via R6. That's a higher value, so it's going to ignore that one. R2 can get there at a cost of 7, 6 plus 1. So that's 7 going via R5. And R1 is going to learn that it can get there at a cost of 8 via R3. Okay, so it's tempting to think that we're done at this point because every router has heard of value. But of course this is going to keep going because this information is going to propagate further, and the next time this news is going to propagate this way, this news is going to propagate this way, this news will propagate this way, and so on. So everyone is going to hear more values in the next round. Let me clear that to make it a little bit clearer and see what happens in the next round. So this was the values that I just showed you. Just as an example, R1 had learned, if you remember, that it can get to R8 via R3 at a cost of 8. So it has that value 8 going via R3, for example. Okay, so now what happens, you can see that we've found out all of the 2-hop information. So this is really like the 2-hop information. In the next iteration, we're going to find out the 3-hop information. Let's see what this 3-hop information is. Well, based on this, the ones that are going to change that I've shown in red here, let's focus on those. R2, which previously thought that the lowest cost path was of cost 7 going via R5, it's going to learn about this 3-hop path because R4 is going to advertise to it the value 6. And so it's going to hear about this value that it can get there at a cost of 6 going via R4. So that's going to be its new value, and that's the one here. Similarly, R5 is going to learn about the 3-hop path, which goes via R4. It's going to learn about this one here. So previously, the lowest cost path was of value 6. Now it's going to learn one of value 4, of cost 4, going via R4. So that's this entry here that it just learned about. So the first 3-hop path that was actually lower cost than the 2-hop path. Let's see what happens in the next iteration. In the next iteration of the algorithm, the news is spreading out further to the 4-hop paths. And in the 4-hop paths, for example, R1 is going to learn of the 4-hop path that goes 1, 2, 3, 4, which is of cost 7, because R2 will have propagated on the information that it can get there at a cost of 6. So 6 plus 1 is 7. So if it goes via R2, it can get there at a cost of 7. So that's this one here. R2 has just learned in this next hop that there is an even better path, and we can see this one here. I'm going to draw this one in green to make it a little bit clearer, which goes via here. And that is a cost 1, 2, 3, 4, 5. So it's just learning that it can get there at 5 if it goes via R5. Right? So the interesting thing here is these two bits of information are actually inconsistent because the algorithm hasn't converged. The news of this particular opportunity hasn't made it to R1 yet. So we'll see that happen in the next step. In the next step, R1 is going to learn of the newer value, which is to go via, that it can reach it in a cost of 6, going on this path here, 1, 2, 3, 4, 5, 6, cost of 6, going via R2. Oops, I got a little bit of a mistake there. Okay, that should be via R2. So now it appears that we're done. How do we know that we're done? Well, we can look at it and see that we can't find any lower cost paths. That tells us that we're done. But you could also see that this will finish. It can't go any further so long as we've explored the maximum hop length in the network. And the maximum hop length here, you can see that there's a longer one that goes like this. That's probably about the longest. So that's 1, 2, 3, 4, 5, 6. So that will be another hop for that information to propagate. So it's the longest loop-free path. We know that a path that has a loop in it must have a higher cost, so we're never going to pick that one. So long as we've gone as many hops as the longest loop-free path, we know that we'll finish. The question is, how do we know that we'll end up with the right answer? In fact, there's a couple of questions that are worth asking here. The first one is, what is the maximum runtime of the algorithm? I just told you that. It's going to be the longest loop-free path. It's going to be the hop count of the longest loop-free path. Will the algorithm always converge? Intuitively, it's actually pretty clear that it must converge because we start out with the values infinity, and we only ever replace them with lower values, and we keep reducing the value until the algorithm has run. So we only ever replace a value with a lower cost value, and eventually we should hear from all of our neighbors their lowest cost path, and so eventually we will reach the lowest value and we will converge. So the algorithm will always converge. It's the clever thing about this algorithm. So what happens when link costs change, or when links and routers fail? We'll see an example of that in a minute, when actually things can go wrong when that happens. But in general, it will continue to converge, because when something fails, if a lower cost path should suddenly appear, then it will find it and start using it. Things are a little bit more complicated when things fail and there is no longer a path to somewhere. And I'll show you an example of this right now. This is a well-known problem with the Bellman Ford algorithm, and it's sometimes characterized as bad news travels slowly. Let's see what's going on here. We're going to look at this really simple 4-router network here. They're all connected in a line, and the cost from one router to the next is 1. So nice, simple, trivial example. So initially everything's working fine. We've converged on these values down here. At time 0, we happen to know that we can get to R4. So this is all about the costs to reach R4 in this case. That R1 can get there in a cost of 3. So that's its value if it goes via R2. R2 can get there at a cost of 2. That's this plus this, if it goes via R3. R3 can get there in a cost of 1, and it's directly connected to R4. So everything is good. But then suddenly, the link from 3 to 4 is going to break. So this link over here has broken. What happens next? Well, what's going to happen is they're going to keep advertising their cost. R3 is going to start advertising, hey, I was under the impression that I could get there with a cost of 1 before. That's here. But I don't have that link anymore. I know that that link is broken. But I did hear from R2 that R2 could get there at a cost of 2. Now I am 1 hop away from R2, so therefore I must be able to get there in a cost of 3 if I send my packets to R2. Clearly this is wrong. R3 is delusional. Can't really do that. But because it's hearing this value advertised from R2 that says if you send packets to me, I'll deliver them to R4 at a cost of 2 plus the cost from me to you, and so therefore a cost of 3. R1 doesn't know anything about the failure yet. Let's see what happens in the next step. So the question is, will it eventually converge and settle down on the correct value? So in the next step, because R3 is now advertising its cost as being 3 if it goes via R2, that news is going to reach R2, and R2 is going to say, hey, you were previously saying to me that it was a cost of 3, but you're now, a cost of 1. Now you're telling me it's a cost of 3. So therefore it must be costing me 4 to get there. It's your cost, which was 3 that you were advertising to me, plus the 1. So it's costing me 4 to get there if I go via R3. And you can see what's going to happen is this is going to they're going to gradually keep feeding each other bad information iteratively, and it's going to increase at every step. And this is just going to spiral out of control. So in the next round, R2 is going to say, hey, you're telling me that I can get there at 4 plus the cost from me to you, that's 5, if I send packets to you. And so it goes to 5, and then you know it's going to go to 6, and so on. And it's just going to keep increasing as we go around. This is known as the counting to infinity problem, or bad news travels slowly. There's a fairly simple fix to this, which it seems a bit of a kludge, but we could set into infinity to be some small number and say 16 and stop when you get to a count of 16. If you get to a count of 16, it actually means that there's no path at all. There are various other methods. There's one that's called split horizon. You'll find this described in textbook. Essentially, because R2 received the lowest cost path from R3, it does not advertise that cost to R3. In other words, because R2 was originally receiving that lowest cost path from R3, it doesn't send those advertisements to R3, and so R3 will never think that it can reach R4 via R2. So that's one way. Another one is called split horizon with poison reverse. In this case, R2 will actively advertise infinity to R3. So it says, because I heard the lowest cost path from you, I'm going to actively send you the value infinity, so you will absolutely never think that you can get there via me. So these are kind of fixes to what is really an elegant algorithm, but then in practice it takes quite a few things like this to make it work. Let's take a look at Bellman Ford in practice. Bellman Ford is an example of a distance vector algorithm. In other words, there's a distance vector that is maintained by all of the routers of the distance from them to every other router, and then they iteratively converge on the correct answer. In other words, the correct minimum cost distance. This is an example of, therefore, of a distance vector algorithm and formed the heart of one of the first routing protocols used in the internet called RIP. And the RIP stood for the Routing Information Protocol, and it was used very widely for quite a long time. And this was because it requires very little computation on the routers. It could be calculated in a distributed way, requiring very little burden, computational burden on each of the routers. And we knew that it would eventually converge with a few little fixes here, like the split horizon technique and preventing it from counting to infinity. Over time, though, it was replaced by other algorithms, other techniques that collect together the entire state of the network on each router, and then independently on their own calculate the minimum cost spanning tree. So no longer a distributed algorithm. And we'll see an example of that in another video on Dijkstra's shortest path first algorithm.